Hello everyone! I wanted to give the highlights on the R Programming 2 notes about data cleaning, preparation, and validation, and just get you prepared for the activity that we'll be doing on Wednesday and Thursday. So the focus of this set of slides is basically working with data and getting it into a form where you can do real analytics and talking about some of the complications you can run into. So number one, how can we check to make sure our data is in the right form to do analytics on? And what are some additional complications we have to worry about? Dates, transformations, and then also missing data. So for this set of slides, we really want to be focusing in on points 1 through 4 here. The missing data imputation we'll revisit back at the end of the semester. So let's talk about data validation. So if we just do analytics on data sets that have issues or errors in it, we're going to get junk analytics out. The adage is junk in, junk out, and that's true for analytics. So we need to make sure that our data file is free of errors or logical issues. All right, so how do we go about doing that? Well, our approach is going to be a little bit different depending on if the quantity of interest here is numerical or categorical. Let me load up the Survey '09 dataset in Reg class because this dataset was self-reported by students. They basically filled in questions to a survey, and that's always going to cause issues when people actually input in values on their own accord. So one way to check the integrity of the data is to make sure that the data is the right type of variable. We have categorical variables like gender, we have numerical variables like weight, etc. And one way to easily check to see what type of object something is with the class command. If I run class on the weight column, I find that the result is integer, so they're all just integers here. I could do the class function on the class column, basically telling me what class they are, freshman, junior, etc. And we see that it's treated as a factor. It's not a character, which is a good thing. And in fact, if I look at the global environment, I can scan down and I see that we have an integer, factor, integer, integer, or numerical here, factor, 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 etc. That provides me one way to check for the integrity. If I need something to be integers, well, the class better be integer. If I need something numerical, well, the class better be integer or numerical. If something's a factor, well, it better return factor here. All right, then when we start looking at the data values themselves, trying to see if any don't make any sense, if some are just wrong, if we have missing values, etc. Really, typically the best place to start is just with a summary of the column. So if I look at a summary of the weight column here, I can quickly identify that, sure, I do have some issues. No one weighed 16 pounds, and so this is a column that I want to revisit. I could look at the GPA of different students here. If I just copied and paste this command and run summary here, I know GPAs go between 0 and 4. This range seems perfectly valid. So looking at the minimum and maximum is a good way to just make sure if there are any issues at the extremes. All right, well, what if you need integer data? Well, one thing you can do is you can look at a table of all the unique values with the table command. So one of the questions was the number of days per week you drink alcohol. So it needs to be 0 up through 7, and indeed that's what the responses were. If you have a categorical variable and you're making sure all the levels are spelled correctly, you don't need to merge any of those together, getting a table of the levels of that categorical variable will let you see how often you see each in the data set. So if you see misspellings, if you see duplicate levels that might have additional spaces in the names, etc., you can see that from doing the table or just looking at the levels themselves. So I can say levels of my categorical variable, and that'll give me a vector of the levels as well. And here's where you could see if there are any rogue spaces that have been put in to those names. All right, another way to check integrity if we have numerical data is by looking at a histogram. We know in this case that the summary indicated that all the GPAs were valid between 0 and 4, and looking at the shape of the histogram lets you kind of see, all right, are there any sort of extreme values that you might want to be suspicious of? If I looked at the histogram of the weight variable, which we had seen before, we have some issues at the lower end of the spectrum here. We see that the largest weight, which was in the upper 400s, looks to be somewhat suspicious. It's not an impossible weight, but it's something that we might want to look at a little bit more closely. All right, if we have a categorical variable, well, we can get a visualization of the frequency distribution by looking at a bar plot, doing bar plot on the result of running table of whichever class that we're looking at. So here we see the 4 levels, we see their spellings, and we see how often they appear in the data. All right, so after we spot errors, what do? Well, we need to fix them. So very often we're going to replace the values that exist in the data with something else. So for instance, if I knew that this particular individual, the 45th person in the GPA vector, right now they have a 3.76, but I actually know that that should be a 4.0, how do I change it? Well, I can just refer to that element and then left arrow it to the new value. So I can left arrow that to 4.0, and then if I look to see what it is, it's been updated. All right, well, what if it's just a bogus value? We don't even know what it's supposed to be. Well, we can left arrow that element to be an NA so that R represents it as missing. So if I look right now at this GPA at 3.5, let's imagine that that was just a bogus made-up value. I don't really know what that value was supposed to be. I can replace that with a missing value just by left arrowing NA into it. Now here's one thing you want to keep in mind, this is a really common mistake, is that when you're assigning a value to be missing, the NA is not surrounded by quotations. If you surround it by quotations, it's going to treat it as a word or an expression, and that's not what we want to have happen. We want it to be treated as the essence of missingness. So make sure there's no quotes around NAs. All right, well, we don't have to go through every single value methodically and change values one by one. If we happen to want to change, let's say, values in a certain range or that meet a certain logical condition, well, we can use that which command to help us out. So for instance, there's a column called money in the bank, and if I look at a summary of this column, well, I see some issues. So I see a lot of minus 999s. That's suspicious. Most likely that's a placeholder for just a missing value. Maybe this person doesn't have a bank account. So one thing I could really quickly do if I wanted to replace all negative values, which can't really exist, with NAs, well, all I have to do is inside the square brackets, right after the name of the column, I can use that which command to specify the positions of the elements that I want to be changing. So which survey money in bank less than 0 is going to print out where it finds values that are less than 0. And so if I left arrow that to be NA, that's going to replace all of those negative values with just missing numbers. And so now I see the smallest value in this column is 0. I have a bunch of NAs, etc. Let's imagine that, all right, I don't really think that any person had more than $2 million in the bank. Let's imagine that I really just wanted to replace anything bigger than 10,000, which is 1E4 in scientific notation. What if anything smaller than 0 or bigger than 10,000 I just wanted to replace with missingness? Well, remember that which command accepts more than one condition. The OR is the pipe symbol, the AND is the ampersand symbol. So this command would replace all the values that are negative or the values that are really too big to be realistic with NAs. So now if I look at a summary of this, the maximum value would actually be 10,000 in this case. All right, well, what about errors in categorical variables? Well, this one's a little bit trickier. Let me load up the donor data set and read in the dozer data set because these two data sets have a lot of issues with their categorical variables. So for instance, one thing we might want to do is to change the level of a categorical variable to be something else. If I look at a summary of the gender column in the donor data frame, I have F and M for female and male. I have one entry that's A, who knows what that means, and a bunch of entries that are U, probably for unknown. So what if I wanted to change this A into a U? Well, in order to actually make changes to categorical variables, we have to make changes to the levels vector itself. So if I just look at the levels of the donor gender column, here's my 4 different levels. And if I wanted to combine this A with the U, or basically change A to U, the way that I'm going to do that is to specify the levels vector and then put square brackets right after it to say, hey, I'm going to work with particular elements of this vector, and I'm going to left arrow that to be what I want to change it to be. All right, so in the square brackets, the safest way to go about doing this is to use the which command, because the which command is going to return the positions inside of a vector that meet a certain logical condition. So if I say something like which levels donor gender double equals A in quotes, that's going to go through the levels vector. It'll pick out the elements that match my condition that I'm specifying, which ones are equal to A, and it'll figure out automatically which levels it has to change. In the notes, I do have that you can refer to the levels that you want to be changing in square brackets just with the numbers, the position inside the levels vector itself. But that's a dangerous way to do it because as soon as you make a change to the levels vector, the ordering of the levels might switch around and square bracket 2 might refer to a different level than what it used to after you had manipulated the levels vector. So the safest way is always going to be using the which command, and I will highly recommend you to do this. So this command is going to change the elements of the levels vector, specifically the ones where it finds A's, to be U. And so I see that I've basically transferred over that one A to a U. And notice the U actually comes first alphabetically, or first in the levels vector, whereas before it was last. So that's why in the square brackets, don't ever hard code those numbers, use that which command. All right, another column that has issues. Well, if I look at the urbanicity column, I have a question mark, presumably representing something that's unknown. Unknown happens to be encoded by U here. So same sort of thing. To change that value from a question mark to a U, what I'm going to do is specify the levels vector, modify it itself. I'm going to left arrow some element of it. And specifically inside the square brackets, I'm going to say, all right, well, report back to me the positions where I find question marks. And we're going to left arrow all of those values to U. So we see once again we've replaced the question mark with U, and look, the ordering of the levels has shifted a little bit. All right, every now and then we actually want to be setting levels of the categorical variable to be NAs, to represent missingness. So for instance, the cluster code column, we have a lot of entries, it looks like from 0, 1 up to 53, which probably means something to whoever maintains this data. But then we have this period. Well, it's not obvious which one of these other levels that we should be merging that in with. Maybe we should just replace that with missing just all by itself. All right, so how do we go about doing this? Well, we're going to be left arrowing that level to be NA. No quotes because NA just by itself means missingness. Quotes is going to treat it as a word. And so what I need to do is I need to print out that levels vector and look to see, all right, how is that level represented? And you'll notice it's smart of me to do this because even though when I did summary it looked like that level was just a little period, it's actually a space, then a period. So in my square brackets, my which command is going to reference the levels that equal quote, space, dot, then a quote. So that'll get rid of the dot level to replace it with NAs. And we can do the same thing here. We can actually specify a vector of values that I want to be changing. I'm going to delete this line right here because it's kind of confusing. Let's say that I wanted to change 12, 14, and 18, all of those to be NAs for whatever reason. Well, same sort of thing. Instead of specifying double equals and then a particular level I want to NA, I can use the %n shortcut and give it a vector of values that I all want to change to NA simultaneously. Saves me a bit of typing. I don't have to type out 3 different lines. So I could wipe those levels out. I see that 12 is no more, 14 is no more, 18 is no more. I have a bunch more NAs. All right, so let's say you change levels to NAs. What if you want to change levels into 2 overall categories? Let me go ahead and reset the donut data frame and revisit this cluster code. Let's imagine that specifically I wanted to study the individuals in cluster code 2, 8, 18, 24, and 45. And I just wanted to really recode the elements inside cluster code to be basically like yes or no, or interesting versus not interesting. So how can I quickly code a whole set of levels to be one of 2 things? All right, well, in my notes, I give an example. Here, I'm going to go through a slightly different example, which I think is a bit more efficient. So how am I going to do this? Well, I'm going to create a vector called of.interest. You can call it anything you want. And I'm going to give it the vector of levels that I find interesting, that basically I want to rename to be something important. So this might be buyers, these might be donors, these might be just interesting, whatever I want to name that. Everything else I'm going to be lumping together, and that's what I don't care about. That's the no's, the not interesting, etc. So once I do define that vector, what I'm going to do is I'm going to modify the levels vector of my categorical variable. And first, I'm going to modify the ones that I don't find interesting. So the syntax of this is a little bit weird. We're going to turn on the square brackets to refer to the particular elements of the levels vector here. And inside the which statement, I'm going to have the exclamation point, the bang symbol, and a set of parentheses. And inside those parentheses, I'll have a statement saying, all right, well, let's look at the levels vector and find the elements that are matching any of the elements inside my of.interest vector. So, okay, what is this doing? What's this exclamation point doing? Basically, if I wanted to read this in English, this would be saying, all right, let's dive into the levels of the cluster code column, and let's find whichever levels do not, that's the exclamation point here, do not belong to the values inside my of.interest vector here. So I left arrow that to be not interesting. I can see what this looks like now. All right, those are the ones that I do find interesting. I just need to group those together. So I can just run one more command, dive into that levels vector here, and change the ones that are inside the of.interest vector, which I'd specified. And we'll rename that to interesting in this case. So boom, I've converted into two levels. Great. All right, so what about dates? So we've kind of blazed through all of the validation set. The special note about NAs, not using quotes, really important thing to remember. What about dates? Sometimes we have temporal information inside our data frame, and that requires a little special treatment. By default, R is going to read that in as a character or a factor, and you're going to do a little bit of work to treat it as a date object. So how do we do this? Well, we're going to be using the library called lubridate. If you haven't done install packages, lubridate, do that in the console window. You never want that to appear actually in your RMD files. That'll make it fail when it's trying to knit. So you can always just do that install.packages on the console and press return. Now, you only have to do this one time ever in this entire class. So once that's done, forget about it. You can always load it up with the library. In fact, you need to load it up whenever you want to use it. All right, so let's read in the pets data frame here. This is basically information about animals at a shelter in Austin. So how do we deal with dates? Well, the first thing we need to do is we need to eyeball what the format of the date is, because there's a lot of different ways of presenting date information. In this case, it looks like we have the year first, followed by the month, followed by the day, the hour, the minute, and the second. And you can imagine all 6 of these bits might be present, might be missing. They might mix up the order in some way, shape, or form. You need to know basically how the time information is presented to you in order to correctly convert it into a date object. All right, so what we're going to do is we're going to match up the order that the temporal information is presented to us just with one-letter abbreviations of what that information is. Year is Y, month is M, day is D, hour is H, minute is M, and S is second. Very convenient that they all have separate letters. That order is going to tell us what command we need to use in lubridate to convert the information into a date object. So the way it works is you specify what that command is just by the ordering that you're seeing. An underscore is going to separate basically the major information like year, month, and date from the daily information, the hour, minute, and the second. So we're going to replace the column that has the date information with the date object. So we'll just overwrite the values inside the date time column by running ymd underscore HMS on that column. Great. So now if I look at a summary of it, is treating it as a date object, you'll notice that the class of the object is changed over here. The smallest date, the one farthest back in time, would be this guy right here. The one most recent would be this date right here. All right, so what do we do with this? Time is kind of interesting to analyze. In this context, it might be interesting to see how the number of adoptions or number of events, there's adoptions, there's euthanasia, there's transfers, etc., how the number of events varies, say, over the course of a year. Give me a total number of times I see each of these events for each month in the data. So we can make a bar plot of the month. Now, how do we do that? Well, we can extract the temporal information that we want just with the logically named command. If you want the month out, well, the command is month. If you want the day out, the command is day. If you want the hour out, the command is hour. It's pretty intuitive. So in this case, if I want to make a bar plot of the month, well, I can do table of month of that column. Month will extract all the months. Table will make a frequency table. If I just run that command, I see that I have the numbers 1 through 12. 1's January, 12 is December. And so if I make a bar plot of that, there we go. Now, very often we actually want labels. We don't want 2, 5, 7. We want February, May, July. So we can get those labels out by just adding in the argument label equals true inside the command that we're using to extract the temporal information. So now I have it labeled with month. Unfortunately, the labels are big enough that it's missing a few of them. If you made that plot a little bit bigger, yeah, they're all there. All right, so same sort of thing here. We could look at the bar chart of the day of the month. Maybe certain days tend to have a lot more things going on than others. Here's what it looks like as we go through the month. So about the same until we have this precipitous drop-off on day 31. You might think that's a little bit weird, but there's a reasonable explanation. Not all months have 31 days, so the fact that 31 is less represented than the other days is just a natural byproduct of how we measure the calendar, essentially. All right, what about day of the week? Well, W day is actually the Monday, Tuesday, Wednesday, Thursday, etc. Day just tells you the day of the month here. We can see that most adoptions are on Sunday, Saturday, or most events, adoptions, euthanasia, transfers, deaths, etc., are on Sunday and Saturday, the weekends here. We can make a bar plot of the hour to see, all right, how does it vary over the course of the day? If I just looked at a frequency table of the hour of this information, I would see that, all right, well, here are the hours of the day, kind of like military time. One potential data issue, I have a whole bunch of zeros. Now, zeros midnight. I don't think the shelter is really open at midnight, and there's a lot of events going on here. So maybe this is a representation for, a missing value. Now, I didn't talk about how to deal with missing values in temporal information, and I'm not going to talk about it. You'll have to look that up on your own time. But we do see this data issue here that really should be addressed. But anyway, let's make a bar plot of the results just to visualize it. And we see that, okay, the busiest time is right at around 5 p.m. There's some stuff in the morning, 9, right when the shelter opens. Seems to be pretty busy. Some things sneaking in a little bit before that, a little after that as well. So kind of cool. All right, so we blaze through the date section here. Let's go on to transformations, because very often, and we'll see this a lot in this course, that the data that's been collected is not actually in the most appropriate form to be analyzed. Sometimes we don't want to analyze the original values. Sometimes we might want to analyze the square roots or the logarithms. Why we do this is typically to make the distributions of the variables more symmetric. It tends to be the case that data mining algorithms work better when the distributions of values are roughly symmetric. All right, let me go back to the donor data frame and look at this column, lifetime gift range. Let's get an idea of what the distribution is. And it's completely uninteresting. All the information is compressed into this very left-hand bar. We have no idea how frequent we see these larger lifetime gift ranges. We get a summary. We see a bunch of zeros here. We have a max at 997. And so, all right, data mining algorithm is not going to work all that great with the information presented this way. We want to make this distribution more symmetric. So what we can do is we can create a new column. I'm going to call it log 10 lifetime gift range here. $, that column name that I want to add is the way to do that. And we're going to left arrow that to the transformation of the values that I want to be taking. And the log 10 transformation is really the most common one. I can't do log 10 directly here because I have zeros, and you can't take the log of a 0 that's not defined. So I'm going to add 1 to that just so that I can take the logs. And that's a pretty common trick. You find the smallest value and you add enough so that the smallest value is 1. And that's fine if that doesn't really change most of the values that you see in the data set. Now, is it okay to add 1 in this case? Well, we see a pretty big range from 0 to 997. The median is 10 here. Adding 1 to everything changes some of the values by, a bit from 0 to 1 here. But a lot of values it leaves it relatively unchanged. So we should be okay with that. So let's add that column. Let's look at a histogram now. And we see that it looks a lot nicer. We can see a little bit more structure here. The zeros represent the people that essentially had 0 for the lifetime gift range. We added 1, then took the log, but that's 0. We can get a summary of the new values here. And remember, these are all on the log scale now, and one of the important skills that you're going to have to polish up on is essentially undoing the log. If I see a value of 1.0414, well, what was the original value that resulted in this? How do I unlog a quantity? And unlogging is actually really easy. You just take 10 and raise it to the power of whatever value you're interested in. So for instance, this third quantile here, 75% of the values on the log scale are smaller than 1.2041, 25% or bigger. What does this 1.2 actually correspond to in original kind of values? Well, I take 10 and raise that to that power, and I find that's about a 16. All right, so we blaze through transformations. Adding in a new column is easy. Just put a $ after your data frame, the name of your new column, left arrow that to whatever transformation you're making. If you're doing log transformations, and you will be a lot, make sure you don't have any zeros or negative values. If you do, add in however much you need to make that smallest value a little bit above 0. Maybe the smallest value is 1.1, 0.001. The choice is up to you here. All right, the last thing that this set of notes is talking about that I want you to be responsible for is missing data. Basically trying to determine if there are any patterns in missing this. If there is, sometimes that causes complications to the analysis, and so let's talk about some of this stuff. Well, the nice thing is that if you run the summary command on your data frame or on a particular set of columns, it'll tell you how much missingness is there. So for instance, if I want to look at the donor age, income group, and wealth rating columns of the donor data frame, when I do a summary, boom, it tells us how many missing values we have, how many NAs we have. So that's a quick way to explore the extent of missingness here. There's a cool little trick where you can immediately get the number of just missing values in all the columns with this command called lapply. I'm going to skip over that. I don't really care about that too much. But there's another command called complete cases to also explore missingness. So if you want to know, okay, do I have information for every single row of my data frame, or is at least one of those values missing? Well, complete cases will actually let you know. So if I say complete cases, and let's just look at these three columns, what that outputs is a bunch of trues and falses. True if we had information on all of the columns that is inside the data frame in the argument of complete cases. False if at least one of those is missing. So I could ask myself, okay, well, how many rows have complete information? Well, I can use the output of this command to do this. Why is that the case? Well, it turns out that R treats the logical value true as just the number 1, and the logical value false as the number 0. So I can do something crazy like take the sum of this vector, take a sum of a whole bunch of trues and falses. That's going to work out to be the number of trues basically in the data frame, telling me the number of complete cases, the number of rows, where I have information for all of the columns in the data frame that was passed to complete cases. So in this case, the donor data frame has about 20,000 individuals. I have complete information on about a third of them. There's a lot of missing values present. All right. I would like to know if there are any patterns in missing values. If donor age is missing, am I more likely to have income group missing as well? Are there any patterns, any associations that I should be exploring? Now, this is a chunk of code that you're going to want to be familiar with. The nice thing is this does all the analysis for you. You just have to change the very first line. You need to do data left arrow and then give it your data frame where you want to look for missing value patterns. So here I'm just going to look at these three columns of the donor data frame, and let's just see how this works. We'll need to make sure the A rules library has been loaded up. You might need to install .packages at first. If you haven't done that, you'll have to do that once in the semester. And what we're going to do is we're going to look, using the command inspect, on these rules, these basically patterns that it's finding. So how do we translate this in English? Well, the way that we translate it is we look to see what's on the left and right hand side of the arrow, and it basically gets translated as this. If income group is missing, then wealth rating is also missing. If donor age and wealth rating is missing, then income group is also missing. These are some of the patterns that it's finding that it wanted to report back to you. The number that we look at is a quantity called the lift, because this is telling us essentially how strong that pattern is. So for instance, if I go with this rule right here, if donor age is missing, then income group is missing. All right, well, is that happening a lot? Well, we look at the lift. The lift of 2.4 tells us that these two values are missing together about 2.4 times more likely than we would expect by chance alone. So it looks like, all right, there is some sort of pattern. If donor age is missing, then it seems to be a bit more likely that income group is missing as well. Is the association statistically significant? Okay, 2.4 times more likely than chance seems like a lot, but that might not be statistically significant. I still might be able to explain that just with random chance. These last two commands help me out with that. This last command says true or false if the rule here is statistically significant. True if it is, false if it's not. I could also look at the number right here. If this number is less than 0.05, we say that the rule is statistically significant. So our conclusion is that it does look like that if donor age is missing, you are, quite a bit more likely to also have income group missing than what you would expect just if values were missing completely at random here. So kind of interesting. Last little bit, I don't have this command right now, so I need to type it. MD pattern, which is in the mice library. You might have to install packages that. MD pattern is going to go into a little bit more detail about what these patterns look like. It takes a little bit of a little bit of time to get used to the way this information is presented. So what are all the bits of information? First, let's concentrate on this far left number. This is telling us the number of rows for which this pattern is applicable. So there's 970 rows that have this pattern. Okay, well, what do these numbers mean? 1 means that the value in the column was present. So this means income group was present in these rows, donor age was missing in these rows, and wealth rating was present. So there are 970 rows where we have both income group and wealth rating, but we're missing donor age. This far right number is just the number of missing values in that pattern. So this row down here would say we have about 1,700 rows that are missing all 3 bits of information. There's 3. We have 5,543 rows where we have income group and donor age, but we're missing wealth rating, a total of 1 missing value. If I look at the numbers all the way down in the last row, well, it's just telling us the number of times income group was missing, number of times donor age was missing, and the number of times wealth rating was missing. This number we can just ignore. I think it's the number of rows that have at least 1 missing column, but might not be. All right, so that's how we interpret those patterns. And there we go. That's kind of your brief overview of what this set of notes is all about. Ensuring data integrity, fixing errors when we see them by replacing numerical values with NAs or a different value, manipulating factor levels, dealing with dates, dealing with transformations, and then also exploring the extent of missingness in your data and finding patterns.